here in the room and also in the outside, online. I will make my last course of this week about radiation effects on microelectronics. Today, we will explore, for the first hour, I guess, or even less, the simulation tools we need to predict effects in electronics. And after that, I will show some experiments, real experiments, even some of the experiments also made with Alexis and Sheila in Sevilla and other places. Okay? So from the point of view of simulation, you need to work in 3 levels. Here we have experts here in the room. We have experts at the atomic level. This is nuclear physics, basically. Also, you need to work at the crystalline level, so that's solid-state physics, condensed matter. And you also have to work at the electronic level, because at the end, remember, we are trying to detect, with luck, to solve a design problem. So simulation is useful for data analysis and also for experiment design, as we will see later on, and requires a multi-scale approach using radiation transport software, solid-state interaction software, and electronic circuit response. On terça-feira, Wednesday, we experiment a little with a simplified version of AHDL spectrum. We were experimenting LT spice, okay? But if you have money enough, you have to go to a professional tool like AHDL spectrum. Okay, so I will start from the electronic level. Why? Because for you it's the hardest, okay? So this is a flip-flop. The technical name is a master flip-flop because it comprised two flip-flops, the master and the slave. This is a design with a very good properties for single even upset resistance. Okay, this is the schematic of that device. Don't be afraid by the transistors, okay? Because at the end you have to look not at individual transistors, but at sets of transistors. So basically, this is a node. This is another node. So basically, you are looking at NOT gates. Okay? Those are my references, so references because that was made 20 years ago. Okay, and at the induction, you simulate, as we saw on Wednesday, the effect, putting a current with that temporal profile, where you calculate the nuclear physics comes into the calculation of the charge that the event will produce in the semiconductor. Basically, you consider the LET, the energy transfer to the bulk, and divide by 3.6 electron volts. This will give to you the number of pairs created, and taking into account that every pair has an elementary charge, you know the charge that you put in that formula. TD and TR are properties from the semiconductor, and this is just to get the shape of that pulse. The connection between electrical or electronic design and the nuclear physics is just one of the first publication and studies about the injection current was made here in Brazil by Fernanda Karstenmith and Birth and Vieira. I guess they are in Rio. They are people from Rio de Janeiro, I guess. ¿Dónde? Rio Grande do Sul. Anyway, from here, from Brazil. So basically, they describe in this excellent paper the technique, and if you know enough about the p-n junction, you can locate in the literature those values. Values that were coincident with the ones I used in the simulation using LT spice. So, okay, that's the result of the simulation. In that case, we have a bit flip because we have a change of state. In that case, we have no bit flip. So basically, to analyze the behavior of the whole circuit, you need to put these current sources at every transistor in the design. That's all. In particular, we developed in my group an automatic tool to make that. To present it. We were using AFTU in the RD53 project, etc. But I will not go in that direction. Okay. If you want to use AFTU, send me an email and we will collaborate. That's all. But basically, what AFTU is doing is just automatizing this process of putting sources and analyzing the results following some heuristics nodes. Well, just for you to see the predictions of the schematic, just for you to know which is a layout. Okay, that's a real aspect looking from above of a flip-flop, of a master flip-flop. Basically, those structures are polysilicon metals, and the transistors are here. So that's the whole game. Now you have the whole view of electronics from the very beginning. Okay.
I decided to ask now because I'm not quite sure if it's going to work. I remember that we discussed about the feedback system in the computers. Oh, sorry. And I was wondering about the simulation, and I don't remember all the behavior of the system to say if it was related to the simulation that you just showed us now.
Yeah. In this, sorry. Okay. In this design, you have here one feedback, and there you have. So basically, it's a couple of flops in tandem. That's all. Okay. No, it's a good question because the significant upset in this structure is precisely at Wednesday I showed to you practical ones. Vale. Next, you can also, I will go very fast in this part because this is even more technical. Okay, if you want to simulate total ionization dose in real designs, you need to modify the transistors coming from the library because basically the effect of a TID is to make bad transistors. So you need to define your own library. You take your measurements in the lab using chips with single transistors. You analyze the behavior, then you codify that behavior in a new transistor mode. Okay, for a PMOS, for a CMOS. We did exactly that for LTD because we were in the need of simulating the behavior of the device after a heavy radiation, OTD. So this is just for you to take a glimpse of what is a TID simulation. It's more complicated, it's more elaborated than a very simple single event upset. Okay, because you have to codify in your transistor that the damage caused by the radiation. The name, just for you to get used to the terminology, the name is to use corner models. Okay, because typically when you design a circuit, even without radiation, you need to know how that device, simulated device, behave if temperature is or the bias voltage is changing. So typically this is named as four. So in that case, you have to add more corners. That's all. We tested a lot of devices. We did that during the first and the second year of our collaboration in RD53. From the group from Marseille in France, we are the responsible of codifying the measurements in Virtuoso. Virtuoso is the cadence. Virtuoso is the software the professional software everybody uses in the industry design circuits. Okay? So basically, the procedure is to define a new transistor library in Virtuoso, your radiation. That's all. This is the process of fitting the data, the experimental data, in the library. Those were the experimental results, it in the MMOS, etc. So there is no, I think this is too technical for this course. But anyway, it's good for you to know how it's made, okay? In particular, those are the effects we included in our models. Not only dependence in the threshold from the radiation, but also short effects, because we were using 65 nanometers. It's a technical thing about how a transistor in that scale is working. Also, sub-threshold swing change. Also, the interface traps are considered in the conductivity model, in the conductivity of the PMOS and the conductivity of the MMOS, the rules, the IV rules of those devices, and also a leakage current for MMOS devices. Okay, so basically that was included in the library. Implemented in Virtuoso. The first version was up to 500 megarad. The second one was up to 1 gigarad. Tells about how to include that library in the Virtuoso suite. Sorry for the delay, but the thing is going very slow. So here you have the final result. Basically, when you are making your design, instead of taking from the library a conventional transistor, a NRAD or a PRAD transistor. That's all. And then you analyze the behavior or the dynamics of the circuit with those TID affected simulations. Sure, they coincide with the results in the experiments, and in particular, this was a circuit simulation. We designed a ring oscillator. It's very simple to see effects in a ring TID effects in a ring oscillator, basically because the frequency became dependent on the amount of those. So it is the first system test you make in your library, and it was good enough to use and to every design, every intellectual property block in RD53 has passed this test before going to irradiation. We irradiated in Legnaro, using and in Padova, using X-ray machines, and also in Zagreb, using the gamma facility there. Okay, the next thing is now you are expert designers. Okay, you know how to transform a very good design into an irradiated design. Just using the correct libraries and just using this trick of putting everywhere sources of current pulses. Going from electronics to the interface between solid state and nuclear physics, you need to calculate, to use radiation transport. Basically, you need to calculate the total stopping power, okay? Which part is going to ionizing and which part is going to non-ionizing, using, for example, SRIM, or using, for example, GM4. I prefer by far SRIM because it's faster. At the end, the predictions coming from SRIM or coming from GM4 are not good enough in the lab. So go to the SRIM, it's free, you can download the SRIM. I think everybody here has worked with SRIM. But remember, this radiation transport is just to define the amount of charge created in the bulk when the track closes, or accumulated in the oxide again when the track closes. That's all. So we are at this moment calculating at the end, the end of this calculation is just QC, charge created. So those are details. This is the paper from Ziegler. RIM is a software created by only one person. It's very good, and it was used during more than 30 years. It was refined during more than 30 years in the foundry that IBM had in the US, in New Jersey. And because they were interested in the diffusion of dopants in silicon is made with a small accelerator shooting ions against the silicon. So they were interested from the very beginning, not for consideration of TID, but for manufacturing consideration. So the SRIM is very acceptable. Considering all the physics we were doing in the past century, in the 30s and the 40s, particularly in the industry. One of the most surprising, I will make the question, who is the industry using by far the accelerators? Which industry? Electronics industry, okay? Because we use ion accelerator for implantation. And in particular, the companies manufacturing accelerators use electrostatic, low energy, for your standards, low energy accelerators. So if you want to get a decent job in accelerators, you have to go to the foundries. This is a typical SRIM simulation to know the amount of charge deposited in the substrate, but you have to consider that the particle has to cross a lot of metallizations. I showed to you the layout of a master flip-flop, and basically it was covered by metals. Okay, so you need to make this. You go to the information from the foundry, and if you are lucky enough, and if you have paid for that information, then you have the knowledge of the thickness. You design several layer models, and then you throw a lot of string simulations to know more or less how much energy is deposited in the bulk. It's a Monte Carlo. That's a three-dimensional view of the same calculation. Okay. If you want to go even more precise, I do not recommend that. It's good for getting and for getting published, but it's a lot of effort, and the precision you gain is not worth of. Okay, you need to make a three-dimensional model of the metallization. It's exactly the same device. Okay, it took me 3 months to put that three-dimensional. Yes. Because GM4, the starting point of GM4 is not the list of physics, but model. So you need a full model with all the bells and whistles, and then you invoke the physics list from the GM4. Okay, then you make your program and blah, blah, blah. This is the energy deposited for an experiment in those years I was interested in, oxygen 18 MeV, but I think it was published in Japan, but I think it's not worth the effort. Okay? Not because GM4, because the need of making exactly. Nowadays, in those years, there were no software to make that automatically. Nowadays, there are software that automatize this thing, but I insist, it's not worth the effort. In the level of, okay, this level, it's not in yeah, sure. The question is that we in CMS use EM4 to model the 4 pi detector, but at a level of centimeters, not at a level of micrometers. So the amount of work here is not worth it. But anyway, you can do it. From there, in GM4, you need a PIT project. The thing important in what GM4 adds to this calculation is the lateral expansion of the track only. Again, considering that you are shooting at dices of square micrometers, is not worth the effort. But anyway, I did it one time in my life. That's all. With that, if you are interested in the device again, or you are making a PhD, for example, then you need to go from the solid state physics, from the nuclear physics to the solid state physics. The name of the tool is Centaurus TCAD or Silvaco. It's up to you. There are other possibilities. But anyway, what any TCAD solves is that set of equations, considering that the currents come from the drift diffusion. There are other models, and they solve that equations in geometry of the model by meshing the device and using analysis. So basically, it's a kind of hydrodynamic model. For what? For having a heavy ion ionization model with all the details at the level of the solid state. It's complicated. I showed you on past Wednesday the final result of this work, but I will not elaborate. Sorry for the delay again. Those are the possible calculations we did in a transistor, in a three-dimensional transistor, modeling the heavy ions, the ionization profile coming from part from GM4 and part from SRIM. You are familiar with this plot because that was, sorry. You are familiar because I presented this on Wednesday, okay? So after a lot of work, 1 year, okay, you have a model good enough to make preparing an experiment. We still are just making flights of fancy because we are in the simulation stage. Details on the model. Target transistor calibration, because at the end, this has to work as a real transistor when you put the currents there. With different ions, blah, blah, blah. For some reason, okay, and the final result was that the model was refined enough to get a prediction. Then I got my PhD, and I have to pay the dinner for the jury. That was for the tribunal. Okay, that was the end of the story. You can also make a total ionization dose simulation. That work was made with people from the CNM in Barcelona. In particular, we took measurements of a liquid. This is a single transistor. NLDMOS and PLDMOS is a transistor we use for radio frequency in the gigahertz regime. They are transceivers, basically. So those transistors are here, system. And we measure leakage current in the 60 cobalt NIADE at CMAT, one of the most beast of gamma dose radiation in Europe. Okay, so from that we developed a model trying to reproduce the behavior of the charges in the oxide. It's a work, for example, the work that Pedro is doing in our PLGATS with you in the FA. Basically, you go through this looks a lot of time, makes a lot of calculations, and at the end you translate those calculations into a ionization, a charge layering in the device, and you run the simulation. it's published, so you will have access, if you have access to the slides, you will have. This is the TID simulation for calibration. We decided, because it was a very long device, to segment the oxide in sub-elements just to increase the speed of the simulation in the server. It's only a technical thing. So basically, the variation of the gate, the threshold voltage you need to create a channel here was acceptably reproduced by the model. Radiation behavior, and blah, blah, blah. So basically, the take-home message here is that you can, if you have time enough, you are interested for some reason, for designing or whatever, you can also make with TCAD TID simulation. Even with TCAD, you can make also damage simulation. This device was a MOS capacitor. MOS capacitors that were tested in the proton synchrotron at CERN, just for studying how the damage that was made in the framework of the RD50. Okay, in Barcelona, we built several MOS capacitors just to understand the damage with different N in P in N, different techniques of using the silicon, and also with different doping profiles. That was the analysis in the beginning of RD50. So the challenge here was to reproduce in the simulator exactly the same phenomena. It was important in that studies because you can go to the lab and take your measurements, but with the simulator, you can tune your parameters and understand what is happening at the physics levels to take advantage of and to propose design modifications, as we propose, okay? That was in the beginning one of the first works in Spain about if N in P or P in N, changing the doping of the substrate, was enough for the high Lumi. At the end, the answer was N in P, as I told you yesterday. It's published for sure. Everything here is all work. Okay, that was the device. Those were the conditions in the experiment. An analysis of how the device's behavior, the behavior of the device when you have different levels of damage and different levels of total ionization dose, because total ionization dose in that case was a nuisance, hiding the results because we were interested in the crystalline damage. Okay. This is Thalia. This is exactly the CV measurement you are doing right now. It's also reproduced in the first, if we launch simulations for TID in that capacitor, because we were to get to rid of that effect, because we were interested in the damage. Those are oxide fixed charge and interface traps. The plot is moving in this direction with TID. And the DDD, we are moving the plot in this direction, in the vertical direction. Okay, so first we analyze the TD, we published. For the DDD, we use, we became long-lasting friends. But this is the PhD of Michael Moll. Okay, I work with him in work at CERN. And this is the very well-known in CMS, the Hamburg model. Because we were testing basically the Hamburg model in those years. Nowadays, everybody in any CMS simulation, it says Hamburg model, and everybody says, oh, okay, that's the Hamburg model. Okay, we made the translation from simulation, from measurements to simulations, etc. And this was reproduced in TICAD. Okay, so we propose even to use these capacitors as displacement damage. So we are not able to patent because it's impossible to patent a MOS capacitor. But I remember a phone call from a company in the US I read your paper, it's very interesting. Are you interested in working with us? No? Okay, you are free to use that, and yes, that's free hardware, not free software, free hardware. Okay, how do you, a point to consider if you are interested in TICAD, how do you introduce damage effects in TICAD? Basically, you have to include different trap models in the device. What we are discussing during 7 years, we are still discussing, okay? But more or less, we get a consensus on the displacement damage, how to put into TICAD, and CMS, there is a CMS note in collaboration with Atlas, 2014 or so, on how to simulate these things for CMS and for Atlas. Models, simulations, etc. Doesn't matter. The conclusions. Displacement damage effects on most capacitors induce a significant reduction in the capacitance value, but in this vertical direction. Okay? In the case of TD, it's in the horizontal direction. So you can distinguish between both. That was a reason to propose why not to use most capacitor, they are used now, to know about the displacement damage. It's very useful when you are in a hard neutron environment. For example, if you are interested in sending a probe to study the sun, because it was used. Not my work, but this effect, because you can distinguish very simple, in a very simple way, between DDD. That was the idea of the most capacitor. Okay, let's go to detectors, also known as diodes. Okay, don't forget that when you speak about detectors, the time about diodes. We use segmented diodes. Why segmented diodes? Because we are looking for special information, where the particle was hitting in the device. Okay, one of the simplest things you can do is to make strips. There you have the typical results from a strip and at the beginning of the semester. In that epoch, we were using P in N. The readout still is. We were reading holes instead of electrons. Nowadays, we will read electrons. That's the meaning of N in P implies reading electrons. P in N implies reading holes. It was presented by Michael in my university because we have invited Michael a lot of times. Just for you to know what is a single-sided strip detector, you have to look at one single-sided strip detector. So you have a bias resistor, okay, just to get the biasing. You have a coupling capacitor. It's very important because if this capacitor is not here, you will saturate immediately the amplifier with the bias. It's critical. And remember, the signal is so fast that basically it will go through the capacitor because the signal lasts 10 nanoseconds or so. So in terms of electronics, it's extremely high frequency signal. But in physics, we work in the time side, not in the frequency side. But at the end, it's the same. Okay? So it was an issue to develop these polysilicon resistors. If you go to the Franz Hartmann's book, there is a thoroughly discussion about which is the better biasing of this kind of detector, because it was also the result of a lot of discussions in RD50. So basically, I'm showing you practical results from the RD50 collaboration, our 20 years of working in the field. And for sure, you have to integrate capacitors and resistors, sensor. Okay? So this is the collected charge for a minimum ionizing particle. Remember, I started the presentation calculating basically the LET. The LET from the software is the medium LET, the medium linear or the mean linear energy transfer. But you have to consider Landau fluctuations because at the end, we're speaking about a quantum phenomenon. Okay, so Typically, we use the best of the world, the most probable charge, but the mean charge is here. So take into account that when we use the typical figure, 25,000 electron pair holes, in reality is less than 25. But our minimum ionizing particle is defined as the one that deposits 3.6 femtocoulombs in a 300 micrometer. That's the standard gauge for calibration, okay, in a 300 micrometer thickness of the diode. If you go to an LGAT in 50, you have to divide this by 6. So you will have 6 femtocoulomb. That's the reason with 6 femtocoulomb, the signal is easily confused with noise. So that's the reason to have an internal gain, basically, to compensate the reduction on the charge created with the gain in the device without the noise coming from the electron. Okay. Details about the Landau distribution is in every book of solid-state detectors. But the take-home message here is that don't go too optimistic with that 25,000 charges, okay? Because in reality, it fluctuates. And we made simulations of TICA. Okay, very important to know after a design. This is just for illustration purposes, but it was in a PhD thesis in 2015, also presented by Michael, and it's the electric field configuration of a strip sensor. The most important thing in a ionization chamber, and now I'm speaking about particle physics, in an ionization chamber, the most critical parameter is the homogeneity and the quality of the electric field, okay? Because it is the electric field that is responsible of the separation of positive and electron charges. And your signal is the amount of current generated by the drift of the electron charges, okay? So if your electric field is affected by whatever, then you are degrading the device. That degradation will manifest in reality in several ways. Okay, those are the symptoms. But the reality is that you are destroying the electric field, the homogeneity of the electric field. It was in those years an N-type bulk. Nowadays it's a P-type bulk because we were testing precisely which were better, an N-type or a P-type bulk, N in P or P in N. For the high lumi, in those years it was LHC. This is a cartoon just for you to get an idea of the process in the solid state level. Okay, so basically we are simulating the current density. Those are the electrodes, the readout electrodes in that strip. This is the distribution of charge along the track. Holes will go down, electrons will go up, and it's a MIP impacting at 45 degrees angle. Why this angle? Because that's the angle considering the magnetic field in the CMS. That's the Lorentz factor. Okay, a lot of charge. Charge is starting to move. For that reason, the color is changing. 1.1 nanoseconds, 100 femtoseconds after the initial hit, the initial creation, the creation event. And you can see here that current charges are started to be collected in the electrodes, holes. Because this P in N, we are collecting holes. 1.2, 1.3, 1.4. This took a month of simulation. 1.5. I think that responds to your question about the degree of fidelity of simulations at that scale of CMS is impossible. Okay? 1.7. Still there is charge still in the device, but you can see that there is one of the electrodes, it's the main responsible of collecting the charge. This will be the electrode with a positive signal. The other ones will have bipolar signals, so basically noise. distinguishing at the analysis level which is the electrode with the positive signal, we locate the vertex, or we locate the track or whatever. 2 nanoseconds, 3 nanoseconds. The event is almost finished. Now, the non-relevant electrodes are also affected by a partial collection of charge. Blue means the electric field without interference of the charges created by the event. And this is the signals that your electronics has to condition. Okay? So, in principle, this impact is distributed between 50 to 200 micrometers. Okay? It's a blob. When you speak about statistics in CMS or in Atlas, part of the reason for the statistics come from this uncertainty. Only part. The other comes from fundamental processes. Okay, but take into account that we are measuring, so it's just for you to show that things in reality are always has some error bars. This is one of the effects of the error bars. 1, 2, 3, 4. The 4 are real detections. Okay, but there is only one particle. How you cope with that? Putting more detectors behind. That's all. That's the reason the inner layer is extremely populated with electronics. Well, next endeavor in RD50. We started 2016. Why not? Because the people from the phase upgrade 2, they were writing the book, the big book of the phase upgrade 2, okay? And they were asking to us, can you reduce the material budget, the amount of mass the particle has to cross? Can you? And the answer was, yes, we can. Why? Doing monolithic detectors. A monolithic detector is one detector where the detector is inside the electronics, not on top connected by band bonding. Okay? So this is one of the first simulations of monolithic detectors where the point in those years was to ensure the stability of the biasing of the diodes inside the substrate without affecting the electronics on top. The electronics here is just for simulation to know about the influence of the electronics in the general biasing. Take into account that here you work at 1.8 volts, and from here to there you work in the 100 volts. So it was important to know if the device, once manufactured, was not self-destroying because of the bias. That was the reason of that, those simulations. In particular, that was my work. Okay, so doping profile, reverse engineering, that's you have to go through that, and in particular using secondary ion mass spectrometry to know the doping profiles, because those doping profiles were a secret from any company. Okay, so you have to make reverse engineering. This was the model, the end model of the reach-through diode. Again, take into account that this is the detector. It's reach through because we are biasing through a semiconductor, PN junction. But the point in those simulations, in those years, was to know if this whole device was stable enough, considering that here we have 1.8 volts and there we have 200 volts. That was the reason of those simulations. It was from the design of the detector. Okay, Gaussian doping profiles. You make doping profiles in your TICA. Gaussian doping the IV plot, just to know if the IV plots you look at in the lab, for example, the things you are used to make in cafe, if it's fitting with the model you are putting in TICA. As I said before, the first thing to consider is how the biasing is affecting the electric field, and in particular the current lines. The current lines are the lines followed, as the name implies, by electrons and holes when you are collecting them. Okay, so it was very important to know if the implants, the distance, details like that you need to know before going to fabrication. Remember, when you're making TICAD, it's almost for free. One person, one server, only time. But when you go to the foundry, you need to put real money. Gaussian profiles, and in this case, I was simulating the response to the laser pulse because we had access in those years to a laser in the lab of Michael Moll, and we were testing precisely with the laser before going to the real particle. So it was good, using transient current technique, backplane, different details. Even we made a full, this is just for illustration purposes, but I made a simulation not only of the HBCMOS diode, but also of the electronics. The electronics was simulated in in HDL spectra. In TICAD, you can have access to a SPICE professional version, HDL spectra, and then you can see how this whole device will behave when you hit with a laser pulse or when you hit with a particle. And it worked. Okay? That's, if not, I would not here presenting the results. But basically, this is the output of the charge sensitive amplifier, that's the output of the shaper, and that's the detector response. Just for what? Just to know if the approach was sensible enough before going to the foundry. Okay, very important. Even, this was a tour de force. Even I decided to include also not only the impact of in the HBCMOS, in the diode, but the impact also in the electronics. Why? Because it was exactly the same particle crossing exactly the same device. So why not to consider both effects combined and to see which is the output of the signal. Yeah? This one? Yeah, basically the charge sensitive amplifier is integrating this signal, and you want to recover for ulterior signal processing, you want to recover the shape. That's the reason you use shaper here. Also the shaper, as the shaper is a filter, it takes out any possible electromagnetic interference effect that you will have in any real situation. So that was just a test to know if not only the detector, but the whole chain was sensible, that the design was sensible enough to go further. Same results, but now considering the implications of a single event effect in the electronics at the same time as the detector. Just to know to discriminate in the comparator, threshold, which is the correct signal coming from the detector and which is the parasitic signal coming from the single event effect, because they will appear exactly at the same time, a different femtosecond. Okay, so we built the MPW2 and we decided to go to the lab to test the whole batch of simulations. I have to say that we started with the MPW2 because the MPW, I know YouTube is now recording, okay? But the MPW1 was a total disaster. Yeah, the point is not to avoid disaster. The point is to learn from those disasters, okay? And we learned a lot about the MPW1, but the disaster was not in the simulation phase. The disaster was in the manufacturing phase, because the foundry, Foundry and those years were brand new, and the rules, the design rule checks you have to follow to have an approval design for manufacturing were not stable enough. Basically, they short circuit the whole device. Okay, but in early 50, were good enough to give us more money to continue the development. So one of the first testing was made in the Rudberg Boskovic Institute in Zagreb. I have also microprobes in Sevilla. There are microprobes in other places. But the point here is that they had a wonderful software for PIXE. And we were using PIXE to know where the particles were hitting in every moment. Okay, PIXE is particle-induced X-ray emission. So if you shoot protons, ions, or whatever with against electronics, the first signal is coming in terms of X-rays from the metallizations. And those X-rays can guide you with pinpoint precision where the target of interest is really in the device. So we were to RBI. It was 2021 during the pandemic. Basically, we made several experiments, single even effects in memory cells, because in that chip we put not only detectors, a detector matrix, but also memory cells to test the memory cells we need for signal conditioning in the real matrix. Okay, so it was a test chip, very interesting results that took us our work for a couple of years. That's the RBI. It's very similar to the one you have here in Paulo. Okay, they have a 6 MeV tandem, horizontal one, with several lines. Also a 1 MeV tandem, again with several lines, even shared in between. Even a set RAM in line E9, that's a master equation. You know, you will speak with the people from the facility, and they will gently you have been listening to me about using stream. Now that's a real use of stream, because the first you need to know the particles in that particular facility are able to go through the metallizations. So you need to launch a lot of, first you need to know this profile. That's the profile of metallization layers scattered in the device. Okay, but you have to cross almost every one of them to reach the active area. This is a chip, just for you to know which is a real chip. Okay, that's the plot of a chip previous to sending that layout to the foundry. In fact, that was one of the chips we made in Sevilla. So, target location, very important to use the pixel. Basically, we've finished the corners of every chip with aluminum. So to establish a reference mark, it's very simple to shoot ions in the corners and to look at the X-ray emission, particle-induced X-ray emission, because basically you are looking at in X-rays using the detectors facility. Here is the corner, there is the corner. From there, you can step by step. Remember, we are working at the micrometer scale. You can go step by step following the X-rays you are interested in. Okay? Because locating targets with an optical microscope is not very helpful. It's helpful on corner. After that, you need to go to pixel. This was the real chip. As you can see, basically you see no transistors. You only see passivations and metals, because that's the aspect of a real chip. It's huge bandwidth. That chip was around 2.5 millimeters by 1.3, I guess, millimeters. And there you have the analog pixel matrix. That was our first monolithic detectors working properly. And this is just a set of different memories for analysis of the single even offset in 150 nanometers from L Foundry. and those are the whole details for all the test structures, the pin detectors, etc., that we use because we were testing things for the big chip after the failure of the MPW1. Target. In the memory, this was a collaboration with the people from Marseille, France. Those are typical tricks of the trade to compensate single event upset in one flip-flop. This is a majority voter, okay? This is a majority voter with feedback to recover the original state, and this is a majority voter with clock skew for filtering single event transient. In particular, this and that are used in RD53 because lessons learned from here were applied to RD53. 5 minutes to the break. There are more elaborated schemes. This is the triple redundancy latch with error correction and skew clock, incorporating every solution in only one. And this is even a more elaborate technique. It's called the dice latch. We published recently the whole research. 2 years, Journal of Instrumentation, Fernando, myself, and the people from Marseille. The point here is that you need 2 simultaneous impacts to get a bit flip. If not, the system recovers automatically. Okay? It's an elaboration from the original master-slave technique I showed you slides ago. Because I can speak about gloom and doom the whole week, but at the end you are doing engineering. You need to develop solutions. Neo-stream simulations. Sorry, but the preparation of this kind of experiment needs a lot of stream simulations. In that, this is a real view of the metallization structures we have in the memories, okay, and the damasquinado, the damascene scheme for the metal layers on top. This is, the name is filling density layers. The point was we want to go to the Zagreb facility because they have a good microprobe, they have a good PIXE. We need to know with their panoply, with the set of ions available, if those ions were energetic enough to reach through the metallization layers up to the active zone. So carbon 12 with state of charge of 5 at 20 MeV gives us a LET of 5 MeV. So we were happy and we went there. You also need to have a DEQ system. As you are aware right now, we are developing a small particle physics experiment because you have everything. You have the detectors, you have the parasitic effects, you have the simulation, you will have the analysis later, you have the DEQ, etc. So we use this card. I have one as a memory top of my desk in my office. Just we use that DEQ, beam, sampling beam, that's Luval-NF, the intermediate board to give the bias, and this is the data acquisition, combining an FPGA, a CPLD, a form of FPGA plus a microcontroller. This is the trigger mode for the PS at CERN, and this was the continuous mode for LBI. Here you can see the whole set there, the microprobe, and the chip inside the microprobe vacuum chamber. Okay? We'll make the break right here before disclosing the data. Thanks. Hello, let's continue the second and final session of today. Hello, people online. So we were starting to know about the results of this single event effect testing in Zagreb. Okay. Details about the DAQ we developed for these particular experiments. Okay, this is a detail of the layout of the matrix of memories. Okay, basically we put at several memories, standard cells, dual interlock storage cell, DICEs, enhanced, triple redundancy standard cells. It's a typical experiment to test which structure is better. You are hitting them with a beam of around 50,000 carbon ions per second. So we choose that high flux to test the dices because for turning a bit flip in a dice, remember, you need almost two almost simultaneous hits. So the flux has to be huge. The conclusions we saw even single event effects in several memories. At the end, from this experiment, we decided that in RD53 to put simple TMR. The dices were behaving excellently, but they were too huge to fit the final design. So sometimes you cannot choose the node in the memory. Sometimes you cannot choose the best option because there are other constraints that limit the possibility of using the best. Another of our experiments, detection of neutron-induced reaction in the silicon photodiodes at the Hispanos facility. This experiment in particular was made 2 years ago. Hispanos is a brand new neutron facility in the National Center of Accelerator, and I had the opportunity to make this experiment with Alexis. Now he's a full PhD at Alexis. It was presented in the laboratory Joliot-Curie d'Orsay beginning of 2024. So this is our neutron line. That's the pelletron, the selective magnet, and straight from the pelletron, we have a neutron and target. We use different production targets. I will elaborate in a moment. That's the photodiode matrix experiment where we are shooting the production targets here. We are shooting deuterons through the pipeline towards a PCB with photodiodes and exactly the same beam, but now using an FPGA because we combine in the same week 2 experiments. One to characterize the neutrons effects in silicon. This is not a damage test. It is a single event effect test, but considering that the generation of ions is made in the silicon due to nuclear reactions. Okay, and the same will happen in the silicon of the FPGA. An FPGA, field programmable gate array. It's a circuit full of digital resources for you to implement any digital design that can fit in. Okay, it's very typical. Nowadays, it's very rare to make full digital ASICs because FPGAs are by far cheaper. So if you are interested in a pure digital design, the first option is always an FPGA. We use an FPGA from Intel. The motivation of that experiment was very simple: to get signals and to know if we could reproduce using the 2-photon absorption lasers in the 2-photon absorption regime exactly the same signal from a neutron collision in a photodiode. This was a collaboration with Intel Oregon. Ricardo Ascazubi was participating in this experiment because They were very worried, they are still worried about the susceptibility of FinFETs to this kind of effects, to neutrons. To get neutrons is hard, to make a neutron experiment is hard, but to make a laser experiment is very cheap. Okay, and they have several, they are Intel, they have chips of money in relative to comparison with us. So the point was to choose a small active region photodiode with 20 micrometers of thickness, a commercial one, but very, very thin, just to get a calibration to compare with real circuits, real FinFETs in the lab. This is the Pelletron facility in Sevilla. A lot of ion sources, a buncher, a bion filter, and a pelletron. The buncher and the chopper are responsible to create a temporal structure in the deuterium beam for making neutron time of flight experiments here. And the neutrons are generated impacting deuterons against a copper target filled with more deuterium or without deuterium or with tritium or whatever. Okay, we use the stripping reaction to produce a flux of neutrons. Buncher, the chopper, that's the dump. Details that you can get, for example, in this presentation of the responsible of that facility, that facility in particular, Carlos Guerrero. Panos. This is a detail of the electronics there. Yeah. Those are the reactions. We have several options with lithium, with beryllium. In the case you are interested in the production of different spectra of neutrons. But in our experiment, we decided to use just the stripping because the energy range was huge. Okay? Stripping is the neutron stripping for a deuteron. It is an exothermic reaction, so we could go up to 10 MeV. The answer is this slide. The question was, which kind of targets are you using? Which are your production targets? And we have plenty of the production targets. Lithium, beryllium, copper, just for stripping. We can generate monoenergetic, we can generate full spectrum. In our case, we were interested in full spectrum to collect signals. That was the motivation of this experiment in particular for the industry. This is not a, we learn a lot, okay? But this is an experiment for Intel. This was an experiment for Intel. A detail, because I guess that you could be interested in the target. So you have there a target holder with cooling, deuterium, titanium, or aluminum plus titanium target, beryllium, copper, a lot of, because it's a symbol of changing the production target, the beam. There you have the monoenergetic and broad energy neutron beams. They were calibrated during the past, in 2020, 21, and 22, so the facility is now properly working, and it's open for making experiments. We were one of the first to make an electronics experiment in 2023, basically because we are from the University of Sevilla. National Center of Accelerator is part of the University of Sevilla. And this is just a detail of the spectrum, the monoenergetic and the broad spectrum. Okay, but you have several options to generate neutrons. The amount, the flux is reduced, but the purpose of this line is to make basic physics with neutrons and also to generate single event effects with neutrons, to study this kind of effects. Okay. We make some research about the possible reactions, the cross sections of the reactions. Those were the reactions where we have interest, the production of magnesium, the production of aluminum. It's important because those ions are generated in the silicon, so they will deposit all the in the device. For sure, we made a kinematic, this is for you, okay? A kinematic analysis of, because we need to know which ejectiles in which directions, then to translate this into a stream. So this is a nuclear physics in action, nuclear physics experiment in action, but oriented to detect single event effects. But, there are angles. Yeah, it's a typical using the relativistic kinematics calculator, or even with GM4, but it was very simple. The energies are well reproduced, and the ejection dynamics is well reproduced using conventional tools online. Okay, so basically I was analyzing which ejectiles in which predominant directions just to know the efficiency. From that, I went into a stream, because a stream is not able to reproduce nuclear reactions. It's able to reproduce ions by using a Monte Carlo. So basically, I had to decide which were the most probable ions ejected and in which directions and etc., just to have a profile of ionization in the device to know the signals coming, or to predict the signals coming from the photodiodes. So it was an interesting exercise from the point of view of nuclear physics, ion physics, and now electronics. This is the target, okay? There were pin detectors from Hamamatsu, very important, very thin, 20 micrometers. They are commercial, not very cheap, but they are commercial. So we designed a PCB with the signal conditioning here. Those are not charge-sensitive amplifiers. Those are current amplifiers. We were interested in capture the real signal, not the signal after processing in the electronics. Separating the photodiodes from the powering and from the signal conditioning through some waveguides. Okay, this is very important. Take into account those waveguides, because there is a problem we solved using electromagnetic compatibility technique. But you need to separate the photodiodes from the electronics, because we were interested in the photodiodes. This is an experiment to capture signals, to know and to reproduce those signals using the laser in the Intel labs. The first thing you need is to design your electronics. So we used the LT Spice. It's good, using different models, etc., to know the signals in advance and to know the transformation of the deposited energy into terms of charge and into terms of signals. Okay, from that we were to design the whole PCB, etc. So that's the standard procedure when you start to design an experiment, including of your PCBs. So basically a current signal of 9.28 microamperes, 200 corresponds to, with a deposited energy around 4.5 MeV. Again, responding once again to your question of how you correlate the signals you see, the current you see, with the nuclear physics. So it's there. Combining different tools, different simulation tools, and a lot of calculation. Okay, that's the device. That's a detailed photodiode circuit board. That's the target for our neutrons. Okay. The signal conditioning, the power conditioning. We tested without a problem this system, exactly the same system, at the end-of dump at CERN, without no problem, without no electromagnetic interference problem. And the reason is that the production target in the case of end-of is almost 200 meters away from the dump. So any electromagnetic interference was washed away by the tunnels and the distances. But here, the production is at 5 millimeters from the photodiodes. So the whole possible electromagnetic contamination, in particular coming from the target, will be processed by this and conducted to the signal. That's the naive approach, okay? That's the absolute measurement. You basically see nothing. Why? Because there is electromagnetic interference. produce precisely in the target. You are hitting with deuterons in a copper plate. You get a lot of electrons in that copper plate, and the copper plate is emitting microwaves. Okay, so a naive approach is impossible in that case. Second less naive approach, put an electromagnetic shield, is impossible because your neutrons have to reach the photodiodes. So which is the solution? A differential measurement. The differential measurement, in a differential measurement, we are capturing the signals coming from two diodes. One is inverted, the signal is inverted. It takes 4 nanoseconds in this particular kind, and we use a delay lane in the other photodiode of 4 nanoseconds. And here, in that simple connector, we make the different signal. Okay, just adding currents. And this, then it is possible because if there is no signal, only noise, the noise will be exactly the same here than there. Okay, so when you make the difference between both, you get nothing. Only if there is a hit. The hypothesis is that the hit, there are no simultaneous hits in the 4 photodiodes compatible with the flux. So basically, that's the only possibility to make signals here. So on Wednesday, I was mentioning Jackson. Okay, that's Jackson. So if you want to become an experimental nuclear physicist, you need to know about electromagnetic, what is happening. And this is one of the simplest solutions, but you have to be aware of this kind of. From that photodiode analysis, we tested also with a gamma source, just to be sure that we are coming from neutron reactions, not from ionization, etc. Made a digital signal processing after the data taking to clean signals, etc., with a low-pass filter kernel. And at the end, we published those the photodiode experiments. We can transform the amplitude of the signal into energy deposited. It was consistent with nuclear reactions. So we got the signals we wanted. And nowadays in Intel, Ricardo is doing exactly the same signals in the photodiodes for testing with the laser the FinFETs, considering that he is reproducing a neutron effects in the transistor. The second experiment was very funny. Was the FPGA experiment. The real purpose of this experiment was to demonstrate to Intel that in our Sevilla facility we were capable of making neutron single effects experiments. So the purpose of the experiment was a marketing experiment. Is important when you want to get resources, and probably they will come next year, I guess, to our facilities to make more experiments, because they want to plenty of big time for a full year. Okay, just in case they are interested. In the US, they only have the Lance facility, totally saturated by. So they were looking for cheap facilities with people in the with the knowledge needed for making this kind of experiment. So we decided to use a target FPGA on beam. That's the FPGA in a commercial PCB. Okay, and why not? The control was also done by another FPGA. Why another FPGA? Because the synchronization scheme was easier with two similar, or identical, in fact, FPGA, that using an FPGA and a microcontroller. In this FPGA, in the target, basically we built a RAM memory with the minimum control to avoid any possible effect in the control, and this is out of the beam. Okay, we developed. We are working precisely in that serial automaton, infinite state machines for implementing serial communication scheme. Okay, so this was basically the work of Alexis. and Jorge, okay, for implementing the controlling, the DAQ in this case, and also the target FPGA. This was very simple because the design here is very simple. This was not so simple, that's a memory. And this was, I think it was very funny. I think, anyway. See, because it was an exercise of doing things in an FPGA you typically don't do or don't make in an FPGA. Typically, you don't use an FPGA as a memory. But in our case, we were interested in knowing the behavior of the flip-flops in that FPGA. Because at the end, we were testing the technology. But remember, in that case, in that FPGA, we have static RAMs built in, and we have flip-flops, resources, that you can route as a matrix, a RAM matrix. Okay, so the purpose of this experiment was not to test the commercial SRAM built in the FPGA, because we had the knowledge from Intel, from the very source, okay, but to test precisely the flip-flops in the design. That was the purpose of the experiment, just to say to Intel, we can do that from the nuclear physics, etc., and also from the electronics point of view. That was the funny part. Demonstrate that our team was capable of making this kind of complicated experiments. Okay, but take into account that this is a commercial experiment. Okay, so a detail of the FPGA controller. Alexis was fighting a lot with that part, with the part of the UART, I remember. The memory, schematics reduced, that's a control FPGA, target FPGA during the test in the office, the Alexis office. Details about the testing. This is the internal structure in the target FPGA with some part of the HDL code for implementing a memory. The funny part, not from the nuclear physics, but from the electronics, is that you don't declare a static RAM HDL. It's implicit. It's implicit. So by defect, the FPGA is rooted to be an SRAM. And you have to discover that the hard way. Okay, so we learn a lot about the internal structure of FPGA. I think that for sure you don't know reading the manuals. Details about the top FPGA. Alexis presented this in Radex, I guess, or in SB Micro. In SB Micro. Okay, and now probably it could be a paper, who knows? Details about the finite state machines, controlling the different events. This is just for digital design. And this was the final experiment, okay? For sure, we put the control FPGA under shield. This is a shield against neutrons, not against neutrons and gammas, not against electromagnetic interference. Electromagnetic interference is not an issue when you are doing digital electronics. It wasn't an issue in this particular experiment. So we shoot during a couple of hours a lot of neutrons against the memory cell in that FPGA. And at regular intervals, every couple of minutes or so, we were dumping the numbers in that memory. And we looked using a small Python program you developed, giving us if there were failures, etc. Real time. So analysis was very simple. That FPGA is repeated. Okay, the question is about the combined effects of electromagnetic interference and nuclear effects. This FPGA is sold it was sold, now it's back Altera. As an FPGA, you can fly. So it has internal system for correction of any electromagnetic interference, in particular in the low voltage differential signal amplifiers. So EMC is not a problem. We were not using the LVDS. we were using the input-output digital conventional systems. So in principle, we saw no electromagnetic interference problem there. That it was not an issue. But we have a single event functional interrupt, a full data loss. It was very interesting because the nuclear reaction was happening in the controller of the memory, not in the memory. So, yeah. Not here, not in the control FPGA, but in the controller, in the controller of the memory. Because you need a controller to feed the memory with data and to take out the data. And in that event, precisely, that neutron hit in that automaton. And we got a full data loss. That's, the name is single event functional interrupt, because the device is not destroyed, but you are unable. We had to reprogram, that's the reason is a hot reprogramming of the whole design, and the device was working. Yeah, it's very typical. But this is a real problem in a digital design. If I have a bit flip in a memory, okay, I have lost 1 bit. But if I have a loss in the controller, I have nothing. That's the dreaded single event functional interrupt. Yeah. Very simple. It's very simple. First, they are in different parts of the FPGA. Okay? In the case of a single event offset, the single event offset shows in the memory dump as a change in the dump. But if you get a total loss of the device, the only possible reason is the single event functional interrupt, because the design in the FPGA was as simple as possible. Yeah. Again, very simple. We are looking at single event upsets, not at single event transients. Sure, you have a lot of transients there, but the reading we are doing is insensitive to single event transients. What we are looking at is just ones or zeros coded as F or Zs, because it was easier to look at. In the RAM memory, we implemented. So if you have events in that structure, an F that changed to another thing, etc., then you know it is a single event upset. But if for some reason the device stopped working, that means that the controller is affected, because you cannot send signals to that memory, or you cannot read out. Again, if the device were destroyed, it could be impossible to reconfigure again the device. But we, after the single event functional interrupt, we stopped the beam and not reset, reconfiguring the whole design. And the device started to work perfectly. And there were recoverable bit flips, because the devices are still working. There were no stuck bits. Okay, they are still working in my office, after considering a cooling time to avoid radioactivity in my office. No, I don't have the informational cross-section in that case, because this was not a characterization of the FPGA. That FPGA was characterized by Altera, and in particular, it has internal correction elements for single event upsets. That was one of the reasons to choose precisely that because Intel was selling the product as a product for space. Any product in space need to have EDAC, systems for devices for correcting errors. And for sure, in the static RAMs in the FPGA, the EDACs were working perfectly. But the problem was not with the M9 memory cells built in the device, but with the standard flip-flops you use for finite state machines, or in that particular case, for implementing a RAM with that flip-flops. that were the vulnerable or the sensitive elements in the FPGA. But again, it was a demonstration to Intel that we were capable. If they put money on the table, we will make the full characterization. It's just a matter of having one full week or a couple of weeks or weeks of time to make the experiment. At the moment we are waiting decisions from Intel. At the moment, had some financial problems, so we are just waiting. Conclusions, the photodiode experiments opened the way to more sophisticated, etc. The water straight signal from the neutron. It was published in particular in one of the reliability conferences in the US in 2024. I'm remembering. The scheme is resistant to electromagnetic interference in the case of the photodiode using this differential measurement scheme. And the FPGA, Max 10 FPGA showed no stack bits and the neutron irradiation, and new neutron single event effects are planned depending on the money coming from Intel. Because this was for science, this was not for science. Okay? This was to demonstrate to a company that we were able to make this kind of questions, because now I will present a resume of what I presented in Maranhão along past week. You said to me present again. Questions about single event effects or whatever? Yeah, but we have a delay. You don't have to describe explicitly the memory array. Those are implicit commands in VHDL, and he will, the compiler will interpret that you are looking for the flip-flops without the combinational electronics around. No. That's totally general. That's a standard in the case of in VHDL. Typically, we use Verilog or VHDL to describe finite state machines. And in the case of finite state machines, you have to declare everything. But in this case, we were interested in using not the elements, but in each logical element. And for that reason, I put in the code. Okay, that's all. Because it took us some weeks to discover that we were over programming the VHDL. Okay, that's all. Because if you, in that particular Altera, in that Max 10 Altera in particular, if you declare explicitly a memory, the compiler interprets that you want to use the EM9 inbuilt memory cells, the ones we were not interested in. We were interested in the flip-flops in every logical resource. So it's just a trick of the trade. Remember the question coming from Alexis, this is not working. I was thinking Alexis knows nothing. No, Alexis knew a lot about what he was doing. The silly one was me, because we were over-designing the VHDL. Sometimes happens. So back to CERN. Why monolithic detectors? This was presented as a motivation to the nuclear and particle physics community here in Brazil, just to show them what we are doing in Europe at the moment. Remember, in the previous hour, we were TCAD simulations about the biasing schemes for monolithic detectors. This is a full monolithic detector. The diode is there, depicted with this scheme. and this is the well for the electronics. So the point is that the electronic is floating on top of a capacitor. Any diode properly reverse biased, if there is no particle heating, is basically a capacitor. So you have a severe problem with the grounding of your electronics. This put you some constraints to define the charge-sensitive amplifier. This is the charge-sensitive amplifier. I will not go into details because you are not analog designers, but that's the real trick in monolithics, okay? To design the first charge-sensitive amplifier, because it is the most affected by this floating effect on top of the diode. This was the full saga. We tested the RD50. This was not working. This was almost working. We discovered, again, the hard way, that a crosstalk, it was not electromagnetic interference, it was a crosstalk, the digital lines and the analog lines in the chip, that the noise in the diodes, in the detectors, were increasing, going in that direction. So basically, the digital block, there is no digital block here, but there is a digital processing block there, that it was sending noise, electrical noise, to the analog detectors near to this. We solved the problem in RD50 MPW4, but look at the time sequence. Okay, years when you are pioneering a technology. Why? Because sometimes happens. Okay, details of the difference MPW1, MPW2, MPW3, MPW4. This part of the talk will be devoted to the MPW2, the MPW4, because this thing was tested on past summer, not this summer, 2024 summer at CERN, and today I'm finishing the paper for this. Okay, more details about the MPW4, the protection for the stabilization of the biasing, etc., the efficiencies, whatever. It's a point that the substrate resistivity of a monolithic it has to be extremely huge, okay? Because it's the only way to withstand a bias of 300 volts without destroying by a spark the device. So it is not conventional. It is not we don't build the monolithics on conventional wafers, on extremely on extremely resistance wafers. A detail of the pixel electronics. This is the analog readout, the digital readout now available in the MPW4. We can put a timestamp. That's the design of the electronics of any pixel. That's the pixel looking from above, where the analog front end, the digital electronics has lines well separated, and also shielding lines connected to ground to avoid any crosstalk between the different lines. So this design from the very beginning was taking into consideration electromagnetic interference from the chip, in other parts of the chip. Again, you need to know the Jackson. The DAQ is now more or less standard. The chip is there. That's the Caribou. That's the Caribou. That's the card supporting the chip. The chip has no packaging, and that's the FPGA controlling everything. I know it's frightening in your first impression, and believe me, it's frightening indeed, because there is a lot of work to build that thing. I have only one full system working, and nowadays is in my group labs at CERN. So I have to go to CERN, take out. Okay. The test was using the same RBI microprobe. In that case, we don't not in the E9 line, but the E3 protons 2 MeV, because that was a test for testing a detector, not a test for testing single event effects in a memory. Okay, so the detectors has the minimum metallization on top. With 2 MeV was more than enough. The target is in that target. We had two different front ends because we were testing the design. This one is our more or less conventional front end with a charge-sensitive amplifier, a buffer, comparator with a DAC to trim the threshold. And this was the that was the switch reset pixel, where if the hit is declared as a valid hit, the charge-sensitive amplifier is reset. In principle, it appeared as a good idea. At the end, it was not a good idea because what we wanted with this design was to get fast signals shooting out or cutting the tail of the signal, just to increase the speed, looking for timing. But introduce undesired effects coming from noise and whatever. Anyway, it was an experimental chip. So we were testing a lot of things. We were testing the detectors, we were testing the electronic front end in the matrices, we were testing memories, etc., etc., etc. So take in your memory that the first column is that thing, the second column is that other thing. Okay, we were in the signals, output. Exactly the same. You need to use SRIM to choose the energy of your protons. You control the flux of the protons locally. We are controlling perfectly the flux of protons with this, more or less 200 protons a second. We put a scintillator patch, a gadolinium patch here to make the coarse approximation. After the coarse approximation, we took out the patch and we used the pixel, the particle-induced X-ray emission, just to navigate through the detector matrix. Just a view of the whole experiment with everything in green light, so everything was at least well biased and properly working. That was the window of the beam, the window of the pipeline near to the target. In one of the approaches, we touch the window, we destroy the window, and the rush of air going into the pipeline destroyed the pixel chip. So we will have to start. So it was delicate. Okay, it was a full summer living in Croatia. Zagreb. Just some signals coming from this pixel and the other pixel. One of the advantages, the real reason to use the microprobe in this experiment is that you can point the beam at any place you want. So without damaging any other structure, we were capable of hitting precisely in one pixel or the other. The signals, you can look at the signals in real time, video. That's a particle physics experiment, real time, yes. And also the heat signal from the comparator. Okay. That's a detail of the tandem. This is the pulse height analysis of the hits, one of the pixels, as it has to be, because we connected the output of the chip to the whole DAQ system utility. Okay, so basically those are X-rays, because remember we are hitting with protons into a lot of aluminum, and its X-ray hits are also detected by our pixel. Those are the low energy beams, and in the high energy beams are the signals, real signals coming from the amplifier. This is the halo. Remember, we are hitting into the pixel. If the center is the pixel, surrounding is just metallizations, another pixel not connected in that moment to the DAQ. Why are you looking at halo? Because if an X-ray is in the position here is the beam position. So you have to imagine that my laser is exactly the proton beam hitting there. If it's hitting there and the X-ray is capable of traveling the pixel, the XY system in the accelerator will register that position and with a hit. So you get halos. What is informant to us is that our device is not only capable of registering the ionization coming from protons, huge ionization. In fact, the black peak is inside the device. We choose that way. But we are also capable of detecting X-rays. So it was important to know about the sensitivity of our detector, extremely sensitive. This was the same test in the R4C5. That's a comparison of the R4C5 with the R4C2. The density of impacts, that's the color is number of hits, is reduced in the R4C5. Why? Because the hit was reset here before going to the maximum amplitude. Yeah, totally, because basically we choose that beam is used there for pixel. They use 2 MeV protons because they are most efficient against aluminum layers to generate X-rays. It's a few kilo electron volts the paper, but it's a few kilo electron because it's calibrated. So basically the layer they use as aluminum target to generate pixel has a similar thickness to the metallization of the chip. So the X-rays are basically the same. So calibrate. But the point, as you can see, it's this device has more signal in the X-ray than in the proton. It's not efficient detecting protons because of this feedback. So one of the results of the experiment was to discard that design. Remember, we were testing everything. We were testing electronics, we were testing the detector, because you have to give all your tests in one experiment. If you want more details about the detector, you need another probe. You need lasers, okay? Yeah. For this experiment, in that moment, we had a conventional microsecond pulse laser, right? Or a HTCT laser in 1054 nanometers. Those were the typical lasers you could buy in those years. So we decided to develop our laser. Why? Because we wanted to generate voxels of charge along the whole bulk of the detector. Remember, we are 300 micrometers, 280 micrometers thick detector. So you need extreme precision of focusing, and in particular, you need that your device has to be transparent to the light you are shooting to. Okay. Going back, not to Jackson, but to one of our founding mothers of nuclear physics, Maria Gopper-Mayer. Okay, she was studying this kind of virtual states in nuclear physics, but you can apply exactly the same quantum mechanics in the case of electron dynamics. When you have when you don't have enough energy to excite an electron from the valence band to the conduction band, then you have a transient. You get the photon is absorbed, the electron goes in the middle of the gap and returns to the valence band. It's a transient, blah, 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 lasts attoseconds, so basically you see nothing. You see electrons moving in the semiconductor when those electrons are in the conduction band in an stationary levels. To get those stationary levels, you need basically to double the energy of your photons. Or you can shoot 2 photons in a very short time frame. If you do that, the second photon has to arrive before 1 femtosecond, because that's the lifetime of that state. The electron stays floating in that in terms of momentum. Okay, floating in the momentum space for less than 1 femtosecond, and if while floating there it receives another kick, it will jump the conduction band. So we studied this was in particular my theoretical work. We studied this process This process means that you need not a continuous laser, but a femtosecond laser to have a decent probability of 2 photon jumps. Okay? So doing the math, you have to design a laser with those parameters. We discovered that they were using by the chemical people, the chemistry they were using. And one specific laser, a mode log pulsed laser. This is spectacular from chemistry. That's the typical linear photoelectric effect, where you can see the focusing, that's scintillating light, fluorescent light, coming from the laser, shooting or being illuminated these dye chemicals. And this is exactly the same light coming from the 2-photon absorption. So it's a voxel. The excitation, in that case, the fluorescent light, is coming from a point. If you move the objective, very funny, you can move the point. Okay? You can even draw some stupid sketch using the laser. There, I did it. Sorry. Okay. The math explaining the thing. I will not elaborate. You have there because important nowadays. Free carrier absorption is negligible, reducing the powering, the energy below 1 nanojoule. And the critical point is the wavelength, because this is where the silicon has a linear photoelectric effect. Beyond that, the silicon is transparent. Transparent with the exception of the focal point, where the intensity is so high that this term is dominant. Okay? If alpha is that regime, alpha is basically 0, so you only have that term to explain the carrier generation equation, the absorption. You have to make a lot of quantum electrodynamics in itself. Okay, you do it, and that's the result. So if that's the signature of a 2-photon absorption in your experiment. That's the pulse energy, and if the amount of electron and hole pairs adjust to a parabol, then you are in the 2-photon absorption regime. To measure the electron hole pairs is very simple using a charge sensitive amplifier, because basically you are integrating the current that you can see from the detector. So at the end, your measurement is proportional to the electron hole pairs, as we discussed during the photodiode experiment with neutrons, blah, blah, blah. Simulations, 590 nanometers, 800 nanometers, second photon absorption regime. Okay, so basically what we are looking is this kind of voxels. In that voxel is the electron and holes pair are being generated, and you can move the voxel along the whole. More simulations taking into account the optics and Python, just to know the profile, the amount, how the charge electron and hole pairs are created, and the profile details with real laser parameters. Okay, that is the effect of focusing of the optics in the quality of your point of charge, etc., in the radial profile and in the depth profile. This is not Jackson. A cartoon, another photography from another dye. Okay, that's single photon absorption. You can see the Rayleigh cone because of the focusing optics using Gaussian beams, and also the PA. That's the red laser. That's the near infrared laser, and that's the EPA-TCT, shortwave infrared laser. That's the real profile of the charge carrier density in silicon. Measurements using sketch technique. I will not elaborate, but it's possible to take real measurements. That's the 3-dimensional resolution tool. I will show you the results. And this science went into a real company in Spain, Fila, that is now selling the artifact. Okay, so this yes, we were elaborating about that. So another take-home message is, if you develop a really interesting system from the point of view of other applications, money will come. This system amounts to 200,000 euros. Okay? But we got even more than 200,000 euros because it was tested. They use this laser in particular for painting sketches, the trousers. When you see stone-washed trousers, they are not stone-washed. They are laser-washed. Okay? Because you want to make a damage in the fabric without destroying the trouser. So you need a precision, exactly, a pin to just draw something in there. Sometimes applications come from, it's huge, it is huge money. In fact, they sell this kind of lasers to companies, with textile companies. Oh, sorry. The laser, okay, the laser, the anechoic chamber to avoid an electromagnetic interference in the detector. We were in the TPA regime, hurrah. Results in different diodes and for testing and calibrating the tool. TPA. There you can see, and that's a real image of the electric field into the device, because basically the amount of signal you got when you excite the device is proportional to the electric field in the device. So there you can see that in the edges there are no signals because the electric field is basically nil in the edges of the. If you do this experiment properly enough, we did it in the MPW4. We'll go very fast now. That's just a video of the experiment. You will see here the flashes of the laser. Remember, at that wavelength, the silicon is transparent with the exception of the focal point. That's the laser, the middle of the. Signals coming from the detector, it was working. This is also coming from the chip, informing us that the threshold has detected something. So it was working, and from that, pinpointing the laser at different positions. I will not elaborate about the aiming procedure. Okay, we were able to aim. So this is an image. This is an image of the depletion depth of the device. This is very important because it's possible basically to measure the depletion depth in a monolithic pixel. Why? Because you have a lot of parasitic capacitance coming from the electronics. So this is one of the best ways to measure the depletion depth. The depletion depth is related to the charge collection efficiency and also to the capacitance of the detector and the noise and the slew rate. A lot of parameters very important from the point of view of the quality of the signal you get. In that case, the laser was on the back shooting in that direction, and this is a tomography of the. This is just for detecting reflection from the metals, because the distribution of metals was different, just to take into account weighting signals coming from the reflections and coming from the silicon. There, those shadows, these images are showing the quality of the electric field at different depths. Obviously, if you are near to the electronics, the quality of your electric field is negligible because you are not in the detector, so you see shadows. This is not an optical image. This is a combination of the XY position of the laser, the XYZ position of the focal point, plus the amplitude of the signal recorded from the detector. And you can see the precision of the method because we are looking at shadows of the electronics, because the electronics produces no signal. Okay? That's in the middle, so the field is very homogeneous as it's intended, and this is the end, in that depth, that's the end of the detector. Beyond that, we got no signal because we were out of the depletion depth. So basically, you can literally look into the electric field. Those are of the electric field. And that's all because we were very happy, and I think it's time to close the session. Okay? And that's all. Thanks for your attention. Questions from the audience? Yeah, you have only seconds to make a question. It's now or never. Okay, time is up. Questions from the questions from the audience, in the external audience? No questions? Thanks again for your patience. No? No? Thanks again for your patience, and I hope to see you again next year.